The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI Web Sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Our next presenter is Dr. Khayat. He's a professor at the Missouri University of Science and Technology, and he's going to present use of fiber-reinforced self-consolidating concrete for the repair of reinforced concrete beams. Welcome, Kamal.
Thank you, Chelik. Good afternoon. Because Chelik already showed my presentation, there will not be a lot of pictures from job sites. So this is what you get to when you are in academia. You're given the last presentation of the day and no job sites. Anyways, I enjoyed all the presentation today. It was really nice to see that this technology is finally picking up in the area of repair rehabilitation, which is a very nice niche market for ACC. So Kamal Khayat from Missouri University of Science and Technology, but also with the University of Sherbrooke. And the work I'm presenting here was done within the industrial chair of high performance concrete with adapted rheology that has been going on for 5 years at Sherbrooke. My co-author is a PhD student which is just finishing his PhD and has been working for 5 years on this project, the performance of fiber-reinforced SCC in structural repair applications. So I'll try to give you an overview of the project. But this is really something that started back in 1995. I think it was probably the first application of repair of ACC. And this is in downtown Sherbrooke, Quebec, where we worked with the city of Sherbrooke to give us some elements that needed some repair. And typically an element like this, which is at the entrance of a parking garage, that is subjected to a lot of de-icing salt, scaling, and corrosion reinforcement at the joint, which was leaking, is very, very typical of damage. And normally what you would do is you would remove all the contaminated concrete, and then you would use shotcrete. In some cases, fiber-reinforced shotcrete. And in this case, we tried a number of different shotcrete, but also a new technology that was self-consolidating concrete. And I'm sorry I missed the first lecture, but we also had bag materials. You know, none of the producers were making any SCC, so we had bag materials put together, and everything was batched on the job site, all the admixtures in the summer. And we also had, like the previous speaker, many people from the media looking over our shoulder doing this. But you see over here very congested reinforcement, not so much the congestion, but the cover over the rebars. On the other side of the rebars is very, very little. And then you have a surface that is not wet enough, so retention of fluidity is very important, flowability is very important. The formwork has to be very, very grout tight, and it was made grout tight and was tested with water, like Chelik was telling us. And typically, this is typical detailing, and the placement was done on top, where the contractor cored 2 cores of 4 inches. This is about 6 meters. And then you have the bleed holes on the other side of the, so we have always to remember the bleed holes to displace the air and let the air go out. Placement method was very easy. The cone construction, cone inverted, and concrete was cast in one place, and we had the bleed holes to observe and make sure that the concrete is coming on the other side. And to our great surprise, and it worked very well, and it gave very nice surface quality. And so this was back in 1995, and 1997, the Quebec DOT picked up this technology and developed a spec for the use of SCC, especially in repair applications, including some specification for specialty cements, blended cements, ternary cements for this, for durability purposes. And also in 2001, the city of Montreal picked up this after a few projects. And this is a project from 2003 where we were placing SCC for repair. And this was the first time that fibers were incorporated in the repair mix. And the reason for that, and these are synthetic fibers added at very low dosage of 0.25% by volume. And the reason for that is to reduce the crack widths, so they can reduce the need of repair in the future and the need to put the surface sealers more often. So in 2008, we started, along with 17 industrial partners that I will recognize at the end of my presentation, a journey, a 5-year journey, working very closely with industry to develop this new generation of what we call high-performance concrete with adapted rheology. And one of the concretes that we were looking at, developing best practices, design recommendations, was the fiber-reinforced SCC for infrastructure rehabilitation. And again, this was picking up SCC and repair, was becoming the choice of many contractors for various reasons that we saw today, but the use of fibers was really something that was new. So in the work that I'm presenting today, in the PhD thesis, we looked at different type of fibers, both synthetic and metallic fibers. So we had the monofilament fibers, the multifilament fibers, what we refer to as MO and MU, both synthetic. And then we had also the hybrid fibers with by mass 1% polypropylene and 92% by mass steel fibers. And then we have the metallic fibers. All the fibers, especially the steel fibers, were fairly short in distance or in length, like 30 millimeter, because of the congestion that often we would have and the limited spacing of the rebars on both sides in repair applications. So the idea was, how do you incorporate fibers in concrete? How do you test them? What are the mechanical properties? What are the shrinkage characteristics? What is the structural performance? All of that. And like I said, we have 17 industrial partners always pushing us and wanting to know more and more. And the student, it's taking 5 years to finish his work. But these are typical concrete mixtures. We have the reference SCC with that fibers, and this is a steel fiber mixture with 0.5% by volume. So this would be 40 kg per cubic meter of fibers. The water binder ratio don't have to be low. They have to be low enough for durability. The strength is not important. Actually, we don't want the strength to be high because of the shrinkage characteristics and restrained shrinkage. But we use a lot of blended cement. In this case, I combined the slag and silica fume cement, about 25% GGBS and 5% silica fume. And that mixture gives us very good rheology, but also very good durability characteristics. We reduce, whenever we are using fibers, we always have to reduce the volume of the coarse aggregates, and we also have to reduce the maximum size of the aggregate. So we use 3/8 of an inch aggregate, in this case crushed, and we limit that to about 270 liters, so 27.5% of aggregate. All our concretes are air entrained, and the slump flows are higher than what Chelik was talking about, and maybe this is why you don't get always a nice surface. But anyways, we can talk about that. But our slump flows, especially when we have fibers, tend to be higher than the conventional SCC. So I'm not going to present all the results. We'll need a lot more time, but I'm just going to pick up especially on what is highlighted here in red. But the study involved a mixed design using a very specific approach, which is based on the equivalent mortar thickness over the rebars and also combined with the steel fibers. We looked at different test methods, and I'd like to point out some of the test methods that were different than what you would do using standard ACM test, for example, Jering or L-box. We looked at the rheology, the stability, the filling capability, etc. And we also, in some cases, when you are using a lot of fibers, 0.75%, for example, we were not having what we are what we consider SCC. So the concrete was not self-consolidating. I'll show you examples of that. So we have to develop a chapter of the thesis. Well, how do you consolidate that, and how much consolidation is enough? What's the energy, and what's the risk of segregation if you over-consolidate? Because sometimes you're going to get into these super workable concrete, but they are not self-consolidating. We looked at mechanical properties, and today I'll talk about this structural performance, and I'll end up my presentation by talking about something that's just coming out now, tests after a year and a half, which is a flexure creep, which I think is very neat. So workability assessment, different type of workability that we've seen, you've seen, as well as rheology. And then when you look at the slump flow, these are slump flow of different type of fibers. But as we load the fiber, what you have here is the volume of the fiber multiplied by the aspect ratio. So this is what we call a fiber factor. So as you increase either the length of the diameter or increase the volume of the fibers, you will reduce flowability. And in some cases, we added more super, but we started having segregation and blockage. So we have to be very careful to get the right rheology to ensure good flowability. And you see that this is the synthetic fibers, which are the flexible fibers that can flow much easier versus the rigid fibers that are the steel fibers. And in some cases, we get into the 20-inch. So we started at, I think, 29 inches. And you get 20-inch, and that's definitely not SCC. It's at best a super workable concrete. And if you were to take the ASTM gearing and apply that to fiber reinforced concrete, it is very difficult to get any meaningful results. You get a bulging of the concrete where the fiber basically fills the gap over here and prevents the concrete from flowing. So after certain trials, we decided for fiber reinforced concrete, it is best to reduce the number of bars from 16 bars to 8 bars and increase the distance between the bars from 43 millimeter to something that is on the order of 5 to 6 inches, 5 inches, which is 2.5 times the length of the fiber. And when you do that, you get very good behavior, and you can differentiate between mixtures that are flowing well versus those that are not. And we also looked at different testing characteristics, and we found out that the expression of the diameter of the flow divided by the average on the mean height would give us a very nice indication of the passing ability. So here we have 5 different types of fibers, different fiber factors, and all of them basically lie on the same graph. So we can start developing recommendations for testing and acceptance of this type of concrete. So we've looked at rheology, we've looked at filling ability, filling capacity, but one of the tests also that we always like to look at, in addition to segregation resistance, is the surface settlement, which is a very simple test. But we've done a lot of that at Shabrook, and we like that test, and we'd like the value to be limited to 0.5%. So this is a 2-foot column, 8 inches in diameter. We fill it with concrete, and we look using an LVDT or comparator. We look at the surface settlement, which follows, if you would, bleeding, if you're used to bleeding. So these are some of the concretes. Those with the steel fibers being heavier, we see that there's a little bit more settlement, which is normal because of the density. But all of these values are lower than the 0.5 limit that we set for these concretes. So if you were to look at typical characteristics, workability characteristics of the fiber reinforced SCC, and on the left here you have what we call the semi-flowable fiber reinforced SCC. So these are 500 to 600 millimeter diameter versus 600 to 730. And in terms of the V funnel, more than 7 seconds, less than 7 seconds. You have the jaring values, the filling capacity values, and the surface settlement values. All right. Then you can start doing some mechanical properties on the different type of fibers. You can do the flexure strengths and the splitting tensile and the compression test, but the one that is of interest a lot for fiber reinforced concrete is the residual strengths, where you preload your prism over here up to cracking at a certain deflection, I should say, and then using a steel plate that prevents cracking from propagating, and then you remove the plate and you load it again, and you determine the average or the mean residual strengths at 4 specific deformations and multiply it by the stiffness. So that gives you an indication of what is the ability of the fibers to sustain residual load after cracking. We need the fibers after cracking, a piece of macro fibers we are using. So this is the average residual strengths versus the fiber factor. And again, you see the steel fibers, 0.25, 0.50%, 0.75, increasing the residual strengths like they're supposed to. And the synthetic fibers, structural fibers, and the hybrid fibers, they're doing also a very good job. The points where you have the bubbles are mixtures where the fiber factor was high, in this case the volume of the factor, that we were not getting any more self-consolidation. And that's why in some cases the benefit is not linear anymore, because we're starting to entrap some air and reducing the strength of the concrete. And that was very apparent when you do compressive strength. It goes up and then start going down because you're entrapping air because of the lack of consolidation. All right. You look at different properties: slump flow, super demand, the drying shrinkage, this residual strengths, splitting tensile strengths, filling capacity. If you put all of those and then you compare, one of the ways to compare is to do what we call a spider diagram, and then you can express the area over here. So when the area is larger, that means the super demand is the smallest, the shrinkage is the smallest, the strength is the highest, etc. But the larger would be the better. And if you compare your different mixtures, you see that the SCC without fibers had a certain area of 7,000. When you start putting steel fibers, in this case over here, 0.25%, 0.5%, you increase that compared to the non-fibrous SCC. And if you start putting more, then you're starting to suffer because of the lack of consolidation. So again, if you want to correct that, you just have to put some vibration in the mix. And the same thing happened with the other type of fiber. The two structural fibers, what we call structural fibers, did a great job. In this case, the multi-filaments, 0.25, 0.5, 0.75, and the hybrid fibers. So definitely the use of the fibers is improving the mechanical properties, shrinkage characteristics, with the right workability characteristics. So the next step was to look at the structural performance. And here we made some beams. So I come to the beam section. Made some beams to look at the structural performance of those beams. And we did two types of beams: monolithic beams, and we also did some repair beams where in the tension zone we simulated a section that had to be concreted later and tested in flexure and compared to the monolithically cast beam. So here we have different monolithic beams with SCC and different type of fibers. Just one section cast at one time versus a repair using different type of repair schemes. So what we did for the repair ones, we cast a beam about 3/4 of the way. We just left about 125 millimeter, which is 5 inches. That was not cast with any concrete. And then we put some retarder at the surface. We let it set, and then the next day we just use high jet, water jets to expose the aggregate and remove any latents at the surface. And then this gave us a section that was to simulate the repair section. And that was cured properly. And when it was time to cast it, we just have pre-inserted PVC sections like you see over here, 4 inches. And we introduce the SCC by gravity, ensuring that continuous placement without any stopping. And as the concrete comes from the different observation holes, we just plugged it, and that's how we had this 125 millimeter tension zone concreted. So the question was, well, is this repair section going to behave similar as a monolithically cast section, whether it's with fibers or without fibers? And then, of course, every time we prepare the concrete, we look at the fresh characteristics of the concrete. So here you have the different, this would be the SCC, slump flow 720, J-ring 715, etc. L-box 99, which is very, very high. All the values over here, if you're familiar with workability of SCC, you'll be very pleased that all of them were very, very high. So even with fibers, 0.5% fibers, we are achieving filling capacities higher than 90%. L-box value is almost 1, so passing ability, stability is excellent. We also did the last mix, which was using 1.4% fibers, and this was a mortar mix. Wanted to see if you suppress the pea gravel, just use mortar mix, allows you, of course, to use a lot more fibers. Would that give us a better behavior than just the other mixtures with the 3/8 aggregate and less fibers? And then after the proper curing, we did the structural performance, three-way bending. And these are typical results. So you would get a load deflection with 3 types of loads. The first load where the cracking occurred, the load where the steel started to yield, and the ultimate load where the maximum capacity was reached. So this was, we did a couple of different beams. Most of the beams I'm going to present you today were beams with 2 rebars in the tension zone, but some of them we added an extra bar to see if the extra bar would be better than using fibers, or the fibers would be equivalent or better than adding another rebar. So if you compare here, these are the monolithic beams, and these are average of 2 beams. So the different loads, I just put them all here, the 3 different loads. And you see the conventional concrete, this is a 4-inch vibrated concrete, versus the SCC, monolithically cast, and the ultimate load of a steel beam. So we see that the SCC and the Fabris SCC are giving very similar behavior, in most cases a little bit better even than the conventional vibrated concrete. But this is monolithically cast without any repair. And then for the repair ones, these are load deflections. So the first one, the black one, would be conventional concrete. And then we have fibers. These are the 2 types of fibers, the monofilament and the steel fibers at 2 different ratios. And then finally the one that is in blue is this one here is a mortar. So we see that in all cases the load deflection and all the loads and maximum loads and yield loads are very similar in the repair section, what you would expect in monolithically cast section, which is very important, because when you are casting this, especially when you are casting the tension zone and the bleeding, you might get some separation and delamination and propagation of cracks. So it's very important that the structural behavior, whether you are repairing with fibers or you are using monolithical cast beams, are very similar. So in summary, if you compare the 3 levels of loads, conventional concrete, SCC, with 2 rebars versus 3 rebars, these are the monolithic versus the repairs. So everything in color over here to the right are the repairs. And we see again, compared to the SCC without fibers or compared to the conventional concrete, the numbers are very, very similar. It's very hard to say this one did better, but the synthetic fibers, the hybrid fibers, the steel fibers are all doing a very good job in terms of structural performance of these beams. The crack width is very important. So we have here the conventional concrete, the crack opening in the tension zone versus load, and those was using fibers, synthetic, steel, the hybrid, and the sections that are even reinforced with more fibers with the mortar. So the use of the fiber is reducing the crack widths and allowing higher loads for a certain crack width. And then using these graphs, you can start looking at toughness and stiffness responses. And then again, all the fibers are giving us very similar load deflection, very similar energy that is needed to crack the concrete. Load deflection, lateral deflection. Again, if anything, the repair sections are giving us better performance than the monolithic, and all the fibers are doing a good job. And when you compare the cracking patterns, always when we had the fibers, the cracking patterns were more favorable. This is, for example, the steel, 0.5% versus monolithical cast beam, conventional concrete. You get crushing and spalling of the concrete and large cracks versus smaller cracks and very little crushing of the concrete. And you can see it here going from conventional concrete to SCC was 0.3%, 0.5%, and this is the extreme going only mortar with very high fibers. All right. Then you can look at different characteristics. And here we're comparing the structural performance, overall structural performance. And we see all the steel beams, 0.3%, 0.5% fibers, did a lot better than the monolithic concrete, whether it's SCC or whether it is conventional concrete. Similar to adding another bar in the tension zone, which made it more congested, but that's giving similar results. In terms of structural performance, the use of the synthetic fibers also improved the performance, but not as much as the steel fibers. All right, the last part, and I'm not going to show you a lot of results, but this is just coming very, very fresh out of our testing program, is a new type of behavior that is a flexure creep. So we're all familiar with creep under compression, but this is creep under tension, and not only under tension, but under flexure. So we are putting what we call mirror type of beams in a frame with a cantilever where there's a load suspended, applying a certain load on the beams. So there's a central load over here, and causing the beams to be under suspended load for a very long period of time. And we are looking at the deformation of the concrete, of the steel, the strains, under sustained load for over a year. And we tested, in this case, the specimens or the type of fibers that were the most favorable to us, which were the steel fibers and one of the two synthetics. Both of them were very good. We tested this one. So what we did is, at very controlled, you apply a load, and you take your load to a certain magnitude corresponding to, for example, over here at 0.35 of the moment of cracking, and then you crank it up, you apply load number 2, which is the cracking moment, and then another one, load number 3, which is 1.4 of moment of cracking. And then after that, you remove the load and you start looking at stress relaxation. Notice the period of time. You have to be very patient to do this type of testing. A very specific test. Took us a long time to develop this. But you look at the strains in the concrete, and again, the strains in the concrete are very important and different from one type of the fiber versus another one. And you look at the strains in the steel, and then you start doing comparisons. So here we are comparing the structural performance of beams under long-term deformation. Among others, we're looking at the crack widths, and we start to compare different type of fibers, and I'll show the results in the conclusion. And then we had a third beam, so there were always two beams, but a third beam after a year and a half, we tested it in flexure, and we look also at the different structural response. So we can compare the instantaneous deflection characteristics versus the long-term deflection. And the findings are, out of what I presented, I'll try to present quickly, is that we feel that the fiber-reinforced SCC is exhibiting good performance, both in the fresh concrete stage and the hardened concrete stage, and is suitable for repair applications to reduce crack widths and improve durability, and especially reduce the restraint shrinkage that we also tested that I did not show. The repair of the beams, or the repair beams, exhibited better overall structural performance than the monolithically cast beams, which was a surprise to us. You would think that the monolithically cast would be better, but even the repair, given the excellent characteristics of the concrete, gave us equal or even better performance. The steel fibers gave us the best overall performance. This is not a big surprise. 0.3 of 0.5%, still getting self-consolidation properties. And I must say also, when you have a 5-inch repair zone and you are placing concrete, you get alignment of the fibers in that. And that's really very, very important to improve the performance of the concrete. The incorporation of the steel fibers can decrease mid-span deflection up to 25%, the strain in the concrete up to 30%, and the crack width up to 80%, which is very, very significant. And then in terms of flexural creep, which I presented, we see that the performance of the flexural creep is very similar to the performance of the concrete under instantaneous static loading, and also very similar to what we were able to learn also by doing the restraint shrinkage, the ring test in terms of time to cracking, crack widths, and the different strains that are developed, as well as the drying shrinkage and the autogenous shrinkage. So they are all related, these properties. And we found out, again, in terms of flexure creep, that overall performance in long-term deformation was better by at least 25% when we were using steel fibers. In conclusion, I'd like to acknowledge the people who have supported this study, and this is the INSERC Industrial Chair on High-Performance Concrete with Adapted Rheology, the 17 partners that you see over here, in addition to INSERC, which is our national science foundation, if you would, in Canada and University of Shelburne. Thank you very much.
Thank you very much. It's 6 o'clock. I think it's